Hi, in this video we're going to take a look at integer constructors, and we'll also discuss numerical bases like base 2, base 16, those kinds of things. And we'll do this video in two parts. It gets a little long, so in this part we'll do the theoretical parts of the video, and in the second video we'll switch to the code. Okay, so an integer is really just an object like everything else in Python. And an integer is an instance of the int class. So an int class, being a class, provides constructors. And we have two constructors in the int class. One constructor takes a single parameter, and that parameter should be a numerical value. So something like a float, or a decimal, or a fraction, things like that, or even an integer. And then the second constructor takes a string and a second optional parameter. And we'll discuss that in a minute. So obviously we can call the constructor this way. We can say a equals int 10. So we pass 10 into the constructor. That's an int. And that will result in a being equal to 10. So we generally don't call it this way. We just say a equals 10. Right? We use the literal expression instead. Obviously we can pass in negative numbers. That works just fine. Now we can pass in other numerical data types. So for example, if we pass in a float, okay, so a equals int of 10.9, well, what happens is that we're going to lose some information, right? 10.9, we cannot convert that without data loss into an integer. And what happens is that it gets truncated. Only the integer portion is retained, and everything after the decimal point is tossed out. So in this case, a would be actually equal to 10. Same thing with a negative number, we get a truncation, and so we end up with negative 10. So this is a truncation, not a floor, as we saw in some earlier videos. This is truncation. Now we'll discuss that in more detail in the videos on floats, and we'll look at alternative ways of converting floats to integers, because you may want to, instead of having 10.9, maybe you want to say, hey, if I convert 10.9 to an int, I want it to be 11. Maybe I want to round up, right? So we'll look at that in more detail. Now, Booleans are actually integral numerical types. You remember when we looked at the Python hierarchy in an earlier video, Booleans are also numbers. So true will actually be equal to 1. When we do int of true, we pass true into the constructor, then a will be equal to 1, and false will be 0. And again, we'll look into that in a lot more detail in the videos on Booleans. Also, we can pass in decimals, we can pass in fractions, and so on. So if we take int of decimal 10.9, well, the same thing's going to happen. We're going to have a loss of data. It's going to do a truncation, and we'll end up with the integer 10. Okay, so you can pass in numerical types into the constructor. But the second constructor takes in a string. Now, the string has to be passable into a number, right? So if you try and pass in a string that can't be passed into a number, well, that's going to be a problem. You probably wouldn't know what it is either, and Python certainly is not going to know. So we can do something like this. A equals int of the string 10. Now you'll notice 10 is just, to us, when we look at that, well, it's the number 10. And Python can actually interpret it that way. And so we end up with a being equal to the integer 10. But what's more interesting is that you can actually specify the base of the number in your string. So you might think that trying to convert the string ABC to an integer isn't going to work. Well, it can. If we're working in base 16, for example, we know that the digits in the hex system go from 0 through F, right? 0 through 9 and A through F. That's what we use to encode 10, 11, 12, 13, 14, and 15, A, B, C, D, E, F. So if we could specify that to Python, then we could actually encode a number like ABC if we could tell Python, hey, this number is in base 16. And so we can do that. So let's take a look first at what happens when we say int of the string 123. It ends up saying this is 123 base 10, right? This is what we get. When we say int of 123 as a string, we get back 123. And, Python and, shows us numbers in base 10. So when used with a string, there is an optional second parameter called base. And this is where you can specify the base of the number that you're providing in the string. And the base has to be between 2 and 36. And we'll see why in just a few seconds. If the base is not specified, then it defaults to 10, which is why in this example, when we said int of string 123, we obtained 123 base 10, right? Because it defaulted to saying, okay, you mean base 10, because you didn't specify a base. But we can specify the base. So in this example here, we can say int of 1010, the string 1010, and base 2. So now we're telling the Python constructor, hey, this string here is a base 2 number. And so when it takes that in, and then if we print out that integer, Python will print out the decimal equivalent of that integer. It will print 10 out, because 1010 base 2 is the same thing as 10 in base 10. Right? So we're not really converting the number, we're just changing its base representation. But it's still the same number, right? Now we don't have to put the 2 just by itself here. We can use a key value argument. So we can say string 1010, comma, base equals 2. I personally prefer using that because it's more explicit in terms of what base we're using, and it's very clear when I'm reading the code that, oh, I've got a different base here. This is not a default of base 10. And so that will result in the same thing, right? 1010 in base 2 is 10 in base 10. Now, we can use also letters as long as we go beyond base 10. So if we're in base 16, the valid letters would be A through F. So this is actually quite correct. It will work. And so A1 to F in base 16 is the same thing as 41263 in base 10. And the case of these letters doesn't matter. You can use uppercase or lowercase. So this would work just as well. All right, we'll get the same number. It's not case sensitive. So Python is able to recognize letters that we can use to encode digits in different bases. And it uses 0 through 9 and A through Z. So we have the 10 digits, 0 through 9, and we have 26 characters, A through Z, which means we have a total of 36 characters. This is why the base is limited to 36. So Python will understand that we're going to use 0 through Z to encode numbers in different bases. But it doesn't go beyond that. If you want to go beyond base 36, you have to write your own algorithm. So another example, we can say, what is 534 in base 8? This is how we would create an integer with value 534 base 8, and that would be 348 base 10. If we print this out, Python will print the base 10 version of that integer. It's the same integer, right? 534 base 8 is equal to 348 base 10. But when we print, we get base 10. Same thing, we can print A in base 11, that would be 10 in base 10, right? So here, A is valid in base 11. It would not be valid in base 10. In fact, B is not valid for base 11. Remember, the digits go from 0 through 9, then A through Z. So 0 through A would be valid for base 11, but B would not be valid for base 11. And we'll get a value error. So if you try and do something like that, you will get an exception. And the exception will be a value error, and the message will be something like this: invalid literal for that integer with base 11, and it will tell you what the literal is. Okay. So now you may be asking yourself, well, can we reverse the process? Can we go from a base 10 and can we see what the representation of that number is in some different base? And the answer, of course, is yes. We can go both ways. Now, Python does provide built-in functions to do that. It provides us the bin function, which stands for binary, which is base 2. So for example, if we have bin 10, it will return a string, which will be the binary representation of the base 10 number 10. Now you'll notice it prefixes that string with 0b. That's just basically a way to document that this number contained in this string is a binary number. It also provides us a function for octal, base 8. So if we do oct of 10, we get 0012. Right? So 10 base 10 is the same thing as 12 base 8. It also has the base 16 function, so hexadecimal, hex, and hex of 10 would be 0xa. Now, these just document basically the base of the number. If you were just to see the string 1010, you might not know, maybe even if you knew it was a number, you don't know what base this is in. Is this in base 2, base 10, base 5, right? So this 0b basically helps document these binary, octal, and hex numbers. So you can use them in your string as well, right? You don't have to just say int of a in base 16. You can also say int 0x of a in base 16. That will work the same way, no different. And these prefixes that you see in the strings are consistent with how we can create literal integers in different bases in Python without having to resort to the constructor. So for binary, octal, and hexadecimal, we actually have these prefixes that we can use in literals. So for example, we could say a equals 0b1010. No strings, right? There are no strings, so a is not a string, and we didn't use the int constructor. We just did a literal integer. It's just that it's of type binary. So Python will understand that the number is 1010 base 2, right? So no strings attached there. And so a will be 10. Again, that's the decimal or base 10 representation. If we have a equals 0012, well, that's just 12 in base 8, which again is 10 in base 10. Or 0xa, and again, the a can be uppercase or lowercase, that's not case sensitive. We'll end up with, again, a equals 10 in base 10. So what about other bases? Can we take a base 10 number and can we get its representation in other bases than base 2, base 8, and base 16 that we saw with the built-in functions? And unfortunately, you need custom code for that. Python doesn't provide built-in functions to do so. Now, I'm sure there are a ton of libraries out there that you can get that will do these representations for us. But let's actually do it ourselves. It's a good exercise, and it will also allow us to flex our muscles a little bit with the div and mod operators. So suppose n is a number in base 10, and b is the target base. So we want to change n's representation from base 10 to base b. Well, what does that mean? That means that we want to find a string of digits, a string of base b digits that represent that same number. And remember, in bases we have b to the 0, b to the 1, b to the 2, etc. So these are the slots. And we just want to know what to fill in for each of those slots for that number n. Like 10 in base 10 was 1010 in base 2. So that's what we need to try and figure out. Now I'm going to bring back that familiar equation that we've seen many times before. N equals b times n div b plus n mod b. The only thing is I'm going to rewrite it slightly. I'm just going to bump b over to the right-hand side of the div. So n equals n div b times b plus n mod b. And I'll use it in that format. So it's no different. It's the same equation. But it's a little easier working that way. So let's take a look at an example. Let's say we want to convert. See, that's the wrong expression. Let's say we want to represent 232 base 10 in a different base. We're not converting the number. And that's something that people often say, we're going to convert this number into a different base. Technically, we're not converting the number. It's the same number. We're giving it a different representation. Okay, it's a different base. And then we have an encoding that maps digits to possibly characters as well. So it's a representation of the number. We haven't converted the number. It's still the same thing. And at the end of the day, it's always a binary number inside our computer. So what we want to do is we want to find out what are the digits that we have to put in these different slots, right? These are 5 to the 0, which is 1. 5 to the 1 is 5, 25, 125. So we want to know 232 is what in base 5? Well, let's use that equation. So let's start with 232. That is 232 div 5 times 5 plus 232 mod 5. Same equation as before. So if we calculate that out, we get that this is equal to 46 times 5 plus 2. Now I'm going to rewrite this slightly to make it more evident what's happening. 46 times 5, well, 5 is the same thing as 5 to the 1, and I'll put square brackets around it, plus 2. Well, 2 is the same thing as 2 times 1, and 1 is 5 to the 0. Right? Anything to the power of 0 is 1. So in fact, what we have is we've obtained the first digit, right, the rightmost digit of our number 232, but in base 5. And the second digit would be 46, right? We have 46 5s and 2 1s. But 46 is too big for base 5, right? That's too big. We can't say the number is 46 to base 5. The highest digit we can have in base 5 is a 4. So what we're going to do is we're going to take the same formula we have, the same equation, but we're going to apply it to 46. So we're going to apply it to the div, to this first div over here, this number 46. So when we do that, we get this expression, 46 div 5 times 5 plus 46 mod 5 times 5 to the 1 plus, and the remaining terms in the expression. So let's rewrite that slightly, right? Let's do the calculation first. 9 times 5 plus 1, right? 46 div 5 is 9, and 46 mod 5 is 1, times 5 to the 1. So now we're going to multiply that out. So we have 9 times 5 times 5 plus 1 times 5. So if we split that up, we get 9 times 5, which is 9 times 5 squared, plus 1 times 5 plus the remaining expression. And as you'll notice, we now can write our base 5 number this way. We have 9 5 squares, we have 1 5, and 2 units. But again, 9 is too big for base 5. So, well, let's do this again. Right? We're going to keep going. So 9 div 5 times 5 plus 9 mod 5 times 5 squared. We calculate that out. We get 1 times 5 plus 4, right, times 5 squared. If we expand that, we get 1 times 5 cubed plus 4 times 5 squared plus the remaining terms of the expression. So now, if we have our number here in base 5, we have 1 4 1 2, and we're good, right? 1 is okay. 1 is a valid digit in base 5. So we could stop right here. This is our number in base 5. 232 base 10 is 1412 in base 5. But let's take a look at the pattern now. So the first number here was the first mod that we did, right? We took 232 mod 5. The second number here was the second mod, which was the mod 5 of the first div, right? So it was 232 div 5 mod 5, because 232 div 5 is 46, and then we took 46 mod 5, was the second mod here. That gave us a 1. The next one was the third mod that we took. So you can see we're just taking the mod results and we're using those as the digits. The only thing is that this one here was our last div. It's not a mod. And we want to write an algorithm as simply as possible, and it's okay, we could do it this way. We say, okay, we just keep repeating the mods until the div's value falls below the greatest digit allowed for a base. We could do that. We'll have to put some if statements, we'll need a loop and then some if statements in there. But let's take a look at what happens if we go one step further and take that equation again, but to the 1. So we have 1 div 5 times 5 plus 1 mod 5 times 5 cubed plus the remaining terms of the expression, and we end up with 0 times 5 to the 4 plus 1 times 5 to the 3, etc. So now our number is 1412, and each of those numbers, each of those digits is being populated by mods. So that's a little more consistent. That's good. And then this 0 here in the div, well, we can use that as a stop. We can say, hey, if we reach a div of 0, stop. Stop processing. We don't need to go any further. We're good, right? We're done. So let's look at what the algorithm would look like to change the base. So suppose n is our base 10 number. Let's assume it's a positive number. We'll deal with negative numbers just now. It's really not complicated. We have to just take the sign out, keep it, and then we can put it back in later. And we'll assume the base is greater than or equal to 2. If you want to work with negative bases, there's lots of online articles that explains how to work with negative bases and different ways to work with negative bases. There are different algorithms and different approaches. We'll stick to standard, bases, greater than or equal to 2. So the algorithm, well, if the base is less than 2 or n is negative, raise an exception. We're not going to handle those. If n is 0, well, if the number is 0, it's always going to be 0, no matter what the base is, right? So we just return 0. We don't have to worry about it. And we'll return our digits in a list. So we're going to return, that 1, 4, 1, 2 we saw in the previous example. We'll return that as a list, 1, 4, 1, 2. So in this case, I want to return a list that contains the single element 0, not just 0. And here we build our list up. So digits starts as an empty list. And as long as n, which is our number, is greater than 0, well, we do the following calculations. We calculate the mod, which is n mod b, and then we calculate the div and store it back in n. So it's n div b, right? And then we're going to put m at the beginning of the list. Remember, we're building our list from right to left. So remember from the previous example. So we need to put m always in the first position of that list. So we're going to insert m at the first position of the list digits. And we're going to keep repeating this until n, right, becomes 0, until that div becomes 0. And as long as it's non-zero, we're going to take that mod and put it in the digits list at the front. And then we'll return digits. And that's it. That's the base change algorithm very simply. So as an example, if we take 232 base 10 in base 5, we get its representation in base 5 is 1412. That was the example we saw earlier. Now if we look at base 16, let's say we look at 1485 in base 16, the digits will be 5, 12, 13. Right? These are the decimal, the base 10 digits, basically. So that doesn't look like hex to us, right? We would think of 12, wouldn't be 12. It would be some letter, right? If A is 10, then B would be 11, and C would be 12. So there should be C, and 13 should be D, right? So we would think that 1485 base 16 should be 5 CD. Well, that's a representation. That's an encoding. So the algorithm is going to return a list of the digits in the specified base, but we still have to do the encoding. So usually we want to encode things, with letters like A through Z. So we simply need to decide what character we want to use for the various digits in the base. So what character do we want to use for digit 12? Well, maybe we want to use C. But we don't have to use that. Maybe we want to use an exclamation point or an emoji, right? Maybe we want, 12 to be a smiley face and 13 to be a frowny face. That's fine. That's just whatever you want as an encoding. Traditionally, we use A through Z. So let's look at encodings. So typically, as I said, we use 0 through 9 and A through Z for digits that require, that are higher than base 10, that require more than just 10 digits, 0 through 9. But we don't have to use letters. We don't have to use the standard digits either. We can use anything. We just need a map between the digits in a number to a character of our choice, a single character. That way we're able to encode, 10, 11, 12, things that are taking up 2 digits in base 10 into a single digit. So we could go the traditional route, 0 to 0, 9 through 9, and then 10 goes to A, and then 36 goes to Z. Right, so this gives us 36 encodings or 36 encoding maps, right? And hence this is limited to base 36. Now we could refine that. We could say, okay, we're going to use, the capital letters, the uppercase letters, and the lowercase letters to have a different meaning. So it's going to be case sensitive, in which case we've got 26 more characters to work with. So we have the 10 digits, the lowercase 26 characters, and the uppercase 26 characters. So that would take us up to base 62, if my calculations are right. Now again, you can use whatever map you want. If you want to map 0 to an A and 1 to a B, and you want to do that, and 10 you want to put in a, as a pound sign, 11 as an exclamation point, yeah, whatever, up to you. Of course, you need to make sure that whoever's reading your numbers understands what your encoding scheme is. So I want to really make the distinction between changing the base of the number and encoding that sequence of digits. Those are two separate steps, and you don't have to always do both. So Python uses 0 through 9 and A through Z case insensitive, and that's why it's limited to a base of less than or equal to 36. That's all it has for the encoding, right? So your choice of characters to represent the digits is your encoding map. It's basically just a sequence of maps. So let's take a look at how we can do this. Now the simplest way is basically to create a single string with as many characters that you have in your base, or at least that many characters that you have in your base, that will be used to represent the ordinal position. So if you use a string 0 through F, then 0 will represent 0, 9 will represent 9, A will represent 10, B will represent 11, and so on and so forth. So looking at an example, let's say we have a base B, we have a map that has to be at least of that length, and we have our digits. Then the way we're going to do our encoding, we're basically going to take our first digit and we're going to look up the character it corresponds to in the string. So it's going to be map of digits of 0, right? We're just indexing sequences here. So that's the approach we're going to take to do our encoding. Let's take a look at a more concrete example. So let's say we look at base 12, and therefore our map would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, right? Where A would be 10, B would be 11, and C would be 12. Let's say our digits are 4, 11, 3, and 12. That was the sequence, the list of digits that we got back from our previous algorithm. Then the encoding would be 4, B, because 11 is B, 3, because 3 is 3, and C would be because it's 12. 12 corresponds to C, right? So that would be our encoding. So that's going to be the simplest way to create an encoding scheme. So let's look at it. So we have our digits, we have our map. We start with a string that's empty, an encoding string, and then we loop through all the digits in digits, right? So for every D in digits, we look up the character that corresponds to D, right, based on the ordinal position, and we add that to our encoding string, and we're running from left to right now, right? When we loop through digits, we're going from left to right. So remember what plus equals means, right? A plus equals B just means take A plus B and then put it back into A. Now this isn't a very efficient way of doing things, because if you think back to our discussion on strings, those are immutable objects. So we're not appending to encoding every time we run through this loop. We're creating a new string every time. We're saying take encoding plus and concatenate onto it plus map D, which is B. That creates a new string and then reassign it to encoding. So every time we're creating a new string. So not very efficient. A better way of doing this, which we'll see in later sections, we're going to get into that in a lot more detail, would be to do something like this. So if you've seen that before, that's great. If you haven't, don't worry about it. We're going to study that in a lot of detail in some future videos. So we can use a list comprehension, and we're going to take every D in our digits, we're going to map it, and then we'll join it into a single string. Okay, so again, don't worry if you don't know what this means. We'll cover it in much more detail. I just want to point out that, you know, this would not be the preferred way of doing it. You can for small numbers, it really doesn't matter, but this is a more efficient and, you know, probably a better way of looking at it as well. It's better looking code than having, you know, these 3 lines of code. We can do that in one. It's still very expressive. It's very easy to understand what this is doing, especially once we've studied it. And so we'll cover that in detail. Okay, enough for this video. And in the next video, we'll really just skip into the code that we covered in the theory here. So thanks for watching, and I'll see you in a bit.